Hi all, and welcome to the next section of Chapter 11. We're going to be doing two problem sets from 11.3. So get yourself ready for notes and we're going to get started. Now, we're going to talk about equivalence relations. So this is our first new term. And equivalence relation is a relation. So a relation that has all of the properties that we talked about last week. So is reflexive, symmetric, there we go, and transitive. So if something says it's an equivalence relation, you can automatically start out assuming that it is all of those things. Now, what a new important idea with equivalence relations is they have something called equivalence classes. So if we start, so given R is an equivalence relation on a set A, then we would call A like this is with brackets, is the equivalence class containing A in the set. So basically, it's one way that we just start thinking about the different sets of numbers, dividing them up by what number is present. So what this means in terms of an actual set notation is that the equivalence class containing A is equal to all the other elements in A, not other, but elements in general, where X is the first term and A is the second. So you can think about it where it's pointing at, if you're thinking about the arrows, it's pointing at at A. So A is the second element here when we describe it like this. So say A is the set 1, 2, 3, 4, and R is the equivalence relation that expresses that X and Y have the same parity. So write the set R. So we know that it's an equivalence relation. So since it's reflexive, we can just start automatically by writing out all these terms. And I could ask you to prove it's an equivalence relation, but I just give it to you in the setup. So then we know same parity, so 2, 4, symmetric, which would be 4, 2. And then we have 3, 1, and 1, 3. And that's the set R. Now, equivalence classes, now what we can do is start by just writing out, this is what I recommend just at the beginning, is write them all out separately and you're going to notice something. So if we look at our set here, we have 4 elements in A. So these are our equivalence classes. So we're looking for all the numbers that are in an ordered pair where 1 is the second number. So in this case, we see 1, 1, and 3, 1. So this is the set containing 1 and 3. Now, because we're going to put the X value in here. Same with 2. 2, we have 2, 2. Because again, we're basing this on the Y value. So 2 is this one, and then 4, 2. And then the equivalent set is made of the first term. So 2, 4. And what you are going to hopefully see is that the equivalence class of 3 is also 1 and 3, 2 and 4. So when we write the answer to this, we generally only write 1, because here's an important note, is that some equivalence classes are equal. And then we only state 1. because they're the same class. So the equivalence classes in this case, you could write as 1 and 2. And that would be enough to describe both equivalence classes in this relation. Now, number 2, let A equal the set containing A, B, C, D, E. And R is an equivalence relation on A where AD, BC, and ED are all in R. If R has 2 equivalence classes, write the rest of the relation. So what we know here is I'm going to start by writing, we know that there's just 2. So I'm going to start by writing A just because it's the first element. So A will always contain itself because it's reflexive. And then what I'm going to look through with these sets is I am going to say, well, since I know A by the symmetric rule, that implies that DA is also in the set. So here, we know that D is an element of the equivalence class of A. By the transitive property, if we're given, we also know that E, R, D, these two together, we get E, R, D, and D, R, A, and that by the transitive property tells us that E is also in the set A. And that's the end of the suppositions that we can make. The next state we'd go to is B, and we know that, given this information, B is always in its own equivalence set because of the reflexive property. We also know that BRC, which by the symmetric property implies that C is in here. Now, we've gone through everything and it says that there's only 2 equivalence classes. Right? Well, this is fantastic because we also know, so then this would be the equivalent here of C. This would be the equivalent class of D, since D is in there. And E, since E is in there, because by the reflexive property, you're always at least going to have that one buddy in that set. So these are our 2 equivalence classes. Therefore, if I want to write out the set R, I'm going to start with the first, the equivalence class of A, and expand that out. We get AA, and then DA, then EA, just written out as it is, but that's also the equivalence class of D, so DD and AD, and finally E, so ED, next EE, AE, and DE. So those would be the 3 equivalence classes that are all equal for the first one. For B, we get BB and CB. For C, CC, and BC, which would be the set there. All right. If you have questions about that, I know we went through that one relatively quickly, but there is an important idea here that we see in this set. And the idea here is that, again, if it says it has 2, it'll always have itself in there, so that'll help you identify which of these are equivalent classes. Equivalence classes. Last example, show that the relation equivalent in mod 3 is an equivalence relation for the set Z. Describe its equivalence classes. So, now the first thing we want to do is, we've already gone, if you want to show that it's reflexive. So quick review. Right, reflexive implies that x is equivalent to x in mod 3. And for these, I would just use the definition is that we're trying to show that this is equal to 3 times something, where a is an integer, right? This is what we want to show. Well, 0 is equal to 3 times 0, so a is equal to 0. Works for every x value. For symmetric, right, we know that x is equivalent to y in mod 3, which means that x minus y is equal to 3a for some a in the integers. We want to show y minus x. If I reverse the subtraction, that means that this becomes negative 3a, which is y minus x is equal to 3 times negative a. Negative a is also an integer, so it is symmetric. And lastly, transitive. We know that x is equivalent to y in mod 3, and y is equivalent to z in mod 3. So what that means is that x minus y is equal to 3a, and y minus z is equal to 3b, where a and b are integers. Now what we want is x minus z. We want to consider that for the transitive property because we want x is equivalent to z. So I'm just going to use substitution. X by itself is equal to 3a minus y, and z by itself, if we're looking at this section, minus y minus 3b. So then x minus z is equal to 3a. The y's become negative sorry, I'm just doing a little algebra quickly in my head. There we go. I knew I dropped a negative because those should cancel out. So then we end up with 3a plus 3b. My apologies for that slow bit of mathematics. Always check for those negatives. So then a plus b. By closure, a plus b is an integer, so it is also transitive. Now, it also asks you to describe the equivalence classes. So with the equivalence class, when we're talking about mod, what I think about, and this is going to be true all along, is that we're going to start with our first set 0. So that's asking for everything in the integers where x is equivalent to 0 in mod 3. So this would be, so the equivalence class of 0 is all the multiples of 3, so because it has no remainder. So negative 6, negative 3, 0, 3, 6, 9, etc. The next one, 1, would be all the integers where x is equivalent to 1 in mod 3. So in this case, that would be negative 5, negative 2, 1, 4, 7, 10, etc. And 2 would be the remaining section of the integers. So negative 4, negative 1, 2, 5, 8, 11. And what you can see now is we've actually listed all the integers because remember, If I then want to go back to this is 3, this would be the equivalence class 4, since they contain themselves. This is equal to the equivalence class 5, 6, would come back to here, 7, 8, 9, all the way down. So we only have 3 equivalence classes in this problem. Equivalence class of 0, 1, and 2, though of course you could have picked 1, 2, 3, or 3, 4, 5. But I'm just going to pick these since that is what you'd actually see if you did the operation. Let me know if you have questions about anything that you see here about equivalence classes, equivalence relations. I'll be on Zoom, available by email, and then of course you can leave something in Google Classroom.